Okay, this is an example of a typical carbon-13 NMR matching exercise. This is the kind of thing you're going to see on your test. I know this here only has 3. Yours on the test might have 4, it might have 5, but the same principles will apply. Now the first thing you should do is differentiate the spectra by the number of peaks you expect to see. And looking at each of these are all labeled, and you can see that this is going to be 1, 2, 3, 4, and this is 1, 2, 3, 4, and this is 1, 2, 3, 4. And all of these carbons are different in each of these, so you expect to see 4 peaks for each of them. And as we'd expect, each of these diagrams does indeed have 4 peaks. The next thing you should do is differentiate them based on a unique carbon atom. And what I would focus on here is C double bond O. This is the only carbon compound that contains a C double bond O. So I would say that this would be the one where you would look for a C double bond O in the spectrum. Now if we go back to our correlation chart, you see C double bond O's appear at around 200 ppm. And this one would then have a peak at around 200 ppm. So there you go, that would be it here. Neither of these has any peaks in the 200 ppm region. So we've already been able to assign this one to this particular spectrum. The other thing that helps us out are the Q's, and the T's, and the S's. And what we can do is we can actually go ahead and label these. And I could label this as a T, a T, a T, and a Q. So that'd be 3 T's and a Q. This would be a T, a T, a T, and a Q. That's a CH2, a CH2, a CH2, and a CH3. And that would be a Q and 3 T's as well. And this one would be 2 Q's, a T, and an S. And that's what we've got here, 2 Q's, a T, and an S. So all of this is very helpful in figuring out what the compounds are. Now let's look at these two. They have the same kind of spectra. There's not very many differences between the spectra. You've got 1 Q and 3 T's. Let's see how we might differentiate these two particular compounds. So on the next page you see that's what I've done. I've already assigned this compound to this spectrum. Now what I can do is look at these two. And what I'm going to do is I'm going to focus on the peak that is furthest out, furthest downfield in each instance. Now what I told you earlier in the introduction to NMR, C13 NMR, was that the closer a carbon atom is to an electronegative element, the more downfield that carbon will be. So what I'm talking about is we look for the one with the highest ppm. That'll be the one that's closest to the electronegative group. So I know that this peak represents this C that's connected to the O. Likewise, I know that this peak is representing the C that's closest to the N. So again, the carbon that's closest to the electronegative group will have the highest ppm value. It will appear furthest downfield. And you can see the progression of the peaks as well. It goes 1, 2, 3, 4, 1, 2, 3, 4. As we get further away from the electronegative atom, the peaks begin to have smaller and smaller ppm values. And that's a very normal thing to be seeing. Alright, so we've gotten that far. We now need to figure out which of these spectra actually belongs to each compound. And the story will be told by the ppm value of the C directly next to the electronegative atom. Now, since this seed appears around, looks like about, let's see, it's 60, 70, that's 80. It looks like it's around 68 ppm. And you've got this peak here, it looks like it's around 44 ppm. Now, if we go back to our correlation chart, you can see that C's around O's are typically around 60 ppm. And C's connected to N's will be around 40 to 50 ppm. So that's how we'll be able to pick out those two. And I would say that the one with the C connected to the N will have the highest peak at around 44, and one with the C connected to the O will have its peak at around 68. And those two are two good ones, I think, to remember. CO around 60, CN around 40 to 50. And that's a good way to differentiate those two. After we've differentiated them, we've assigned the compounds to the spectra, we can then assign each peak to the numbered peaks in the compounds. Now the way this works for this compound and this one is, like I said before, the peaks that are closest to the electronegative atoms will be furthest downfield, and then as we get further away from the electronegative atom, then the ppm values for those peaks will decrease. So if we go 1, 2, 3, 4, we'll go 1, 2, 3, 4 down here as well. In this case, we have two CH3s, and those will be 1 and 4. Now those can be differentiated on the basis of which one happens to be closer to the C double bond O. As you can see here, 1 is closer to the C double bond O than 4 is, so I would assign this Q as being 1 and I'd assign this Q as being 4. The other two are easy. This one is a single peak and it's a C double bond O, so that one will be labeled 2, and this one is a CH2 and it's a T and it will be labeled 3. So assigning these is not very difficult if you take both chemical shifts and the Q's, the T's, the D's and the S's into account.